Okay, we are continuing the dive into linear algebra. I'm really excited for the next few days worth of content. It's just some of my favorite stuff, and hopefully you'll see why as we get through it. This video will be a little bit shorter. I do want to let you know the next one will be slightly longer, so just plan accordingly. Okay, here it is. I said it was going to be a short video. Now you're like, there must be something else, right? Well, yeah, of course there's details, but like that is the fundamental concept. If you've got that conceptually, you're most of the way there. And then we unpack the details. So we have used matrices previously to represent systems of linear equations, and that's a completely valid application of the concept. Um, We've also at least mentioned that matrices can just represent data sets. You can just have an array of data values and perform actions on that array, and that's valid. And so now we're looking at this idea that matrices represent actions that you do to coordinates or shapes or locations within a space. Let's look at some examples of these different kinds of transformations. So first we have translations with that star, and you're like, where am I being misled here? Well, translations are absolutely legitimate transformations that you can do. A translation means to take a given location or shape and to simply add a constant value to that shape. You're just moving it left or right or up or down or whatever. The reason I have a star is because you don't actually accomplish translations with matrices. I'll show you why in a second. We have scaling transformations. So that is going to take a shape and without distorting the shape at all, it is going to make everything larger or smaller. Complementary to scaling, we have rotation. So rotations are not changing the size or shape of a thing, but they are changing the orientation of a thing. They are going to spin it within the space without distorting it. What's an improper rotation? An improper rotation is a rotation that also contains a mirror image action. It's something that will not just spin the shape around, but will flip it like in a mirror image. You can mix these things. So you could make something larger and then turn it, or you could turn something and then make it smaller. So you can combine these actions. And that's going to be like our main category of sort of simple rotations is scaling and rotation operations. But then there's a whole universe of other options out there. And I'll introduce some of those ideas, but we probably will get into the details more in the homework. One that I will bring up now because it's a word that we encounter a lot in MSc talking about mechanics is the shearing transformation. So this is taking a thing and not just making it larger uniformly, but changing the scale of the different axes relative to each other. So the thing gets like twisted or stretched and not just enlarged or shrunk. Okay. So I mentioned that translations aren't really matrix operations. And there might be some like very wrinkly big brain way to figure out how to express this as matrix operation. I've actually never figured it out myself and I'm too stubborn to look it up. So I'll just say that a translation, you translate a vector by adding a different vector to it. And if it's a uniform translation, then that means you're adding the same vector to all points in the space. You're just taking everything in the space and you're just moving everything by the same constant amount. And that's what a translation is. So shapes are not affected at all. Orientations are not affected at all. It's merely where stuff is. And we do this again by adding a constant vector to all the coordinates and everything in the space. And that's it. So I'm not going to overdo it. We're going to move on. This is something that you've already seen a little bit in the homework. So I just want to formalize it and state it very officially that a matrix operating on a vector gives you another vector as output, assuming that the number of rows and columns of these things, it gives you a legal multiplication. If it's not a legal multiplication, then it just doesn't happen. So in equation form, this is what we're dealing with. We have a matrix M, and it's acting on a vector A. And again, I want to use this language of transformations. that this shows us some action being applied to the vector A. So within the content of this matrix M, those different elements of M give us the information about what kind of transformation is happening. And I'll show you those examples in the next several slides. When that transformation acts on the vector A, that is represented mathematically by saying matrix M times vector A turns it into vector B. That's the product, the result of the multiplication. And thinking about the content of vectors, because a vector is an ordered list of numbers, very often that vector represents a point in space. If we think in 3 dimensions for a second, then that means that the components x, y, and z of the vector, those are the x and y and z coordinates of some point that is living in our 3-dimensional space. So when you have a matrix multiplying this vector, what it's doing is it's giving you a map. It's giving you a set of directions for how to take the x coordinate of a point or an object and to say, what will the new x coordinate of this object be after the transformation? And likewise, the matrix acting on the y coordinate tells you how that y coordinate changes and becomes the new value, so on, so on. So this is telling us how every point in the plane or in the volume or in the whatever dimension we're in, but how every point gets moved to a new point under the action of the transformation. So to write this out with letters, we have some initial point, x initial, y initial, and then a matrix acting on that. You can see here how the multiplication goes. I know people have been practicing matrix multiplication on the homework, and I'm seeing a lot of good work there. So I'm trusting that this is starting to feel a little bit more familiar now. And the action here, when we have these values, non-zero values, A and B and C and D, when you look at how the multiplication works, there's something really important happens, which is that A times X goes into the new X value, sure. B times Y also goes into the new X value. So this B, this upper right off diagonal component of the matrix, this tells you something about mixing between the coordinates. It tells you how much of the original Y value goes into the new X value. That's going to be really significant in a few days. I'm just planting the seed for now. Likewise, C, the bottom left off diagonal element, that tells us how much of the original X value goes into the new Y value. Now, when you apply this to a set of points, then this starts to describe how shapes are transformed under a transformation. So I'm not writing out the matrix here. The particular values aren't the point, but I want to show that if you had some initial shape, blue triangle on the right here, then you can completely describe that shape by a set of vertices, that there were some initial points 1, 1, and 4, 1, and 1, 4, and that gave you all the information you needed to draw the shape. So if you want to see how that shape is transformed, then what you do is you apply your transformation matrix to the vector 1, 1, and the vector 4, 1, and the vector 1, 4. And then that will give you the new corners of the transformed triangle. And that new transformed triangle will have corners at -½ 1 and -3½ 1. And the C point apparently is invariant, as we say, under this transformation. And so it stays in the same place. So the idea is that we could write, knowing these numbers, we could write down the components A, B, C, and D of the transformation matrix that turns blue triangle into red triangle. All right. A while ago, which I mean, like, I guess a whole day ago, I said, hey, we're going to talk more about the meaning of determinants later. Now it's later. When we write the matrix for a transformation, the determinant of that matrix has a very concrete, like tangible, palpable value. I couldn't think of more synonyms for touchable. And that meaning is that the determinant tells you how much the sizes of objects change when they are transformed by that matrix. So you have a transformation acting, we have a matrix representing that transformation, the determinant of the matrix. If it's bigger than 1, it tells you objects get bigger. If it's smaller than 1, it tells you objects get smaller. If it's 0, it tells you that objects collapse or disappear somehow. They like lose dimensionality. And if the determinant is negative, that is showing an improper transformation. It's giving us some kind of mirror image effect in addition to, possibly changing the size in other ways. So in 2 dimensions, size is area. So you have the determinant of your 2 by 2 matrix being the number that tells you if areas get larger or smaller. In 3 dimensions, size is volume. And so the determinant of our 3 by 3 transformation matrix tells you how much bigger or smaller volumes become under the transformation. We don't have kind of like special words for size in more than 3 dimensions. Usually we'll just say something like the 4 volume or the 5 volume to indicate the 4 or 5 or so on dimensional size of a shape. We're not going to do a lot of higher dimensional stuff in this class, so don't like freak out. But if you think it's interesting, then you can say, wow, now I feel smart. Cool. I already said this verbally, but just to reiterate, negative determinants do not mean anything is broken. A negative determinant simply means that the space becomes flipped, that you get a mirror image action as part of the transformation. Okay, cool, great. So that's determinants. Then the inverse of a matrix has a really nice, simple meaning in this way of understanding things. The inverse is just the backward transformation. Instead of, if I go back to my my example here with the triangles, if there was some matrix M that turned blue triangle into red triangle, then the inverse of M is the transformation that takes red triangle and turns it into blue triangle. It's actually simple. It's great. Don't overthink it. That's all there is to it. So saying that more formally, here it is. The matrix, the original matrix transforms Y or X1, Y1, Z1 into new points, X2, Y2, Z2. The inverse is the transformation that takes you back to the first coordinates. This also then makes sense why the inverse matrix should have a determinant that is 1 over the determinant of the original matrix. Because like if the original matrix made things smaller, then the inverse transformation should make things bigger. And so if that original determinant was less than 1, the new determinant should be greater than 1. It all works out. Now, I know some people have some feelings about Math 215. I have feelings about Math 215 also. Mine are mostly positive, but it wasn't a perfect class. One of the things that came up in that class that I really struggled with at first was coordinate transformations. And I don't think they ever magically got better for me. I wish I could promise you that to look forward to. I think it's just something that I eventually did so many times, I kind of became comfortable with it eventually. What I wish I had learned earlier is how to deal with coordinate transformations with matrix math, because that absolutely would have made my life easier. Unfortunately, I got it a couple years later, and by that point, okay, whatever. This isn't my therapy session. Matrix operations and matrix algebra for doing transformations of coordinates definitely are a good thing and make your life better, and I recommend them. So what's going on in this image that's been on the screen? Well, what I'm showing here is a change of coordinates. I'm showing, in this case, a rotation that takes our original horizontal and vertical coordinate system, X for horizontal and Y for vertical. And I'm saying, okay, what if those coordinate axes rotated? What if we wanted to talk about an angled coordinate system instead? You can absolutely do that. What you then need to have is some way to calculate the new coordinates of a point in that new coordinate system. And you can do this with matrices. What you want to do is to find the coordinates of the new point, so P prime is our new point here, relative to the new coordinate axes. So here we've just taken the whole thing and rotated it counterclockwise, or left if you must, but counterclockwise really. I'll let people just kind of read the diagrams for a second. When you look at these in terms of angles, then you can use all of that great right triangle trigonometry that you know with breaking things out into components with sines and cosines as the sides of triangles and work out the particular formulas that tell you how much of each thing in each direction by getting the sides of those triangles. So we're going to talk a lot more about rotations in the next video. I don't want to overdo it here, but I did want to introduce this idea that when you want to change between coordinate systems, you can write a matrix and then act on any vector in the space to find its new coordinates in the new system. Now, where would I use this in material science? Because that sounds like a very math class kind of thing to do. Well, when we are doing crystallography, so I'm thinking crystal structures here, you certainly can write your traditional XYZ coordinates, left, right, up, down, back, forward, but that may not be the thing that makes the most sense if your crystal structure is not cubic. Like, what if you have an orthorhombic crystal structure? Maybe it makes more sense for your coordinate axes to be along the sides of the unit cell in that crystal. This would give you a more natural basis for expressing the locations of different atoms within that cell, because the cell doesn't have cubic symmetry, it has a different symmetry. So compared to maybe what we're naively used to, you might be like, I don't like non-rectangular coordinates. And that's fair. It's okay to have that feeling. But moving into a coordinate system that matches the symmetries of the space you're in will make the calculations easier. So that's just one example that came to mind. Long story short, if you know one set of basis vectors, you can transform it to any other basis by having a matrix for that transformation, and then that lets you see how coordinates of things change. Great. One more example to cover in this video, and then we'll wrap it up, is the idea of a projection. This is not something we'll deal with much in this class. I'm just bringing it up because honestly, I think it's neat, and because it does show up in other less MSE applications. But when we're looking at transformation matrices that are not square, if they change the dimension of the space, then that transformation might look something like this. So in this case, we could say, all right, I have some initial matrix XYZ that is, some initial coordinate XYZ that is three-dimensional, and I'm going to multiply this not square matrix by it, and it'll transform that vector. But it's going to transform that three-dimensional vector into a two-dimensional vector. So it's taking this volume and squishing it down into a plane. This is how we calculate shadows of things, by the way. Now, this also gives us another little bit of justification for why you can't really define the inverse of a matrix that's not square. It's because this transformation is not reversible. You can't calculate the exact volume of a thing in space only knowing what its shadow looks like from a certain perspective. Okay, cool. So why does this matter? Let's wrap it up. Well, one, so I'm actually like a huge video game nerd. I grew up on Nintendo and blah, blah, blah. But when we're calculating graphics on computers, whether it's for games or whether it's for scientific data visualization or whatever your pet project is, maybe you just like computer graphics and movies. Like that's cool too. All of these graphical calculations are done with matrix transformations. We want to find out how rays of light move through a scene. We're doing matrix math. If we want to find out the projection onto the screen, like what does the viewer or the player actually see on their two-dimensional monitor based on the distribution of these three-dimensional models in the simulation space, well, you have to do a projection. So you use that non-square kind of projection matrix that I just showed. So this stuff is all over the place, computer graphics. Very, very powerful. In a MSE example, I mentioned this a little bit when I was introducing some of the linear algebra stuff, but finite element analysis is a very, very important toolkit for understanding solid materials, for understanding distributed three-dimensional structures that occupy volume and have interesting and complicated shapes, because we just can't solve those things by hand. But what we absolutely can do and need to do as part of this finite element calculation is all the little chunks of the object that we break it up into to do calculations on. We need to relate all those coordinate systems to each other. Every little element in the calculation has its like body coordinates, its own little x and y and z axis that it carries with them. And if the shape is complicated and it's twisting and it's rotating, then the coordinates of the different elements might not be the same as each other. And so to relate them to each other, you need these transformation matrices to connect together all the coordinate systems within your body. And that also translates to another loosely MSE adjacent topic, which is also just cool. This is how robots orient themselves. If you think of something like a robotic arm that's able to move around in 3 dimensions, then yes, you can track all the math in some external Cartesian coordinate system, describe everything in X's and Y's and Z's. But that can actually make the math harder when things are rotating and turning and twisting in 3 dimensions. It's often a lot more convenient to have a coordinate system that is carried by the body parts of this robotic arm or leg or whatever it is. And so to understand where that arm is located and how it's oriented in space, you need to keep track of the transformation matrix that takes its coordinate system back to the outsider's coordinate system so that they can exchange information between each other and the robot can do its calculations to figure out how it needs to move in space. Okay, great. So that's my story. I'm sticking to it. Thank you for joining me, and we'll look at rotations in depth next time.